Next Generation Seminar Series is a networking event for early career scholars, juniors, modelers, and epidemiologists working on or interested in mathematical modeling of infectious diseases and other threats to public health. Bienvenue à tous. La série séminaire MFPH Next Generation est un événement pour les chercheurs en début de carrière, les modélisateurs juniors et les épidémiologistes travaillant ou intéressés par la modélisation mathématique des maladies infectieuses et d'autres menaces pour la santé publique. First of all, we wish to acknowledge this land on which the Fields Institute operates for thousands of years. It has been the traditional land of Huron-Wendat, the Seneca, the Mississaugas of the Credit. Today, this meeting place is still the home to many indigenous people from across Turtle Island, and we are grateful to have the opportunity to work on this land. Premièrement, nous souhaitons reconnaître cette terre sur laquelle l'Institut Fields opère depuis des milliers d'années. C'est la terre traditionnelle des Huron-Wendat, des Sénèques, Mississaugas. Aujourd'hui, ce lieu de rencontre abrite encore de nombreux peuples autochtones de tout Turtle Island et nous sommes reconnaissants d'avoir l'opportunité de travailler sur cette terre. Our guest today is Rado Ramasy. He is a PhD student at the School of Public Health of the University of Montréal, ESPOM. After studying medicine in Madagascar, Rado completed a master's degree in epidemiology at the University of Limoges, a master's degree in statistics, modeling, data sciences in health at the Sorbonne University in France. During his training, Rado was able to work in health system of Madagascar, particularly in the fight against malaria. Notre invité aujourd'hui, Rado Ramasy, est doctorant à l'École de santé publique Université Montréal ESPOM. Après des études en médecine à Madagascar, Rado a complété une maîtrise en épidémiologie à l'Université de Limoges, un master en statistique, modélisation et sciences des données en santé à l'Université de la Sorbonne, France. Durant sa formation, Rado a pu travailler dans le système de santé de Madagascar, notamment dans la lutte contre le malaria. His talk will be on multi-level mediation analysis, deciphering the impact of information sources on adherence to restrictive measures during the COVID-19 pandemic. Sa présentation portera sur l'analyse multiniveau de médiation, décrypter l'impact des sources d'information sur le respect des mesures restrictives pendant la pandémie de COVID-19. Rado, the floor is yours. Thank you very much.
Thank you, Idris. Maybe I will start with a disclaimer. Since I am not a mathematician and also the case study we will present here is not finalized yet. So feel free to correct me if I'm saying nonsense, and also feel free to give us some advice for our study. So as Idris said, I will present today a multi-level mediation analysis. And to do so, we will see first the foundation of the mediation analysis, and then the complexity with the multi-level data structure. And we will finish with our case study, which is the trust study. So I wish to start with a few questions. The first one is, do genetic variations affect lung cancer directly or through an affinity for smoking? Does the socioeconomic level of the child affect the health of the adult, mainly because of economic factors? For an educational intervention, should we target the quality of intervention to improve school results? Does a cognitive behavior therapy intervention improve symptoms only through the use of antidepressants? And are the inequalities experienced by people of different races can be partially described by socioeconomic status, genetics, and physical phenotypes? Those are very various questions, but the similarity between them is that there is some association. We want to go in deep details. So the principle of mediation analysis that usually we during our research project, we only focus on the relationship between one exposure or a few exposures and the effect on the outcome. But sometimes we wanted to know if there is an over covariance on the pathway between the relationship between the exposure and the outcome. And for that, we define what we call the mediation structure. When we have a first effect, which is not mediated, is a direct effect, the direct effect of A on Y. And the second one is a mediated effect, which go through another variable on the pathway from A to Y. So to get in more official definition and terms, the mediation analysis can be defined as a set of principles and techniques to help us to identify and quantify the proportion of an effect, the effect of an exposure on an outcome that passes through over causal pathways other than the direct one. And it can help us to improve scientific knowledge, as I said before, to get in depth on some relationship we want to assess, such as the relationship between genetics and cancer. And here we can see that despite the direct effect of some genetic features who can cause cancer, there is also a tendency caused by chromosome 15, who the people with certain trends, certain characteristics are more keen on smoking, so it will aggravate the risk of cancer. The other objective will be to confirm or refute a theory, such as we've been said before, the question about the socioeconomic status of childhood and its impact on the health in adulthood, and the possible pathways through the adult socioeconomic status. And also, the mediation analysis can be motivated by refining intervention, since we can work directly on job insecurity um, to improve psychological distress. We can work instead with the psychological work environment. And also, on the same logic, we can act on a mediator if we can act directly on the exposure. For example, to solve the problems at birth given to assisted reproduction techniques, we can act on the twin and multiple pregnancy instead of stopping the reproduction techniques. So how can we implement that? The thing is that it was an old problem with a traditional method proposed by Baron and Kenny in the 80s, such as we have to modelize the different relationship between A and Y, A and M and Y. So the first one is to regress, to do a regression model for the association for the mediator explained by Y and all of the confounders. So we will have this equation for the mediator. And the second step is to do another model for the outcome to explain it and try to explain it with the exposure, the mediator, and also the confounders. And from these two models, Baron and Kenny proposed that we can estimate the direct effect as the first parameters from the second model. And for the indirect effect, we have to get the information for the mediator model and the effect of the mediator on the outcome model. So we have the beta 1 and theta 2 for the indirect effect. And of course, the total effect will be the sum of the direct and indirect effect. The thing is, since it's always a little bit complicated, um, on our field, it's getting more and more complicated in epidemiology and public health in general. So this traditional approach arises two main problems. The first one is the confusion between mediator and issue. And there is this paradox from the study from the 90s, where some studies find that there is a protective effect of smoking with the infants with low birth weight. And it kind of saying that if you have a low weight newborn, if you are smoking, it will protect you from infant mortality, which is very paradoxal. And this is the perfect example of a mediation structure, since the smoking for the mother will affect the baby weight, and the weight of the baby would affect the mortality. But the thing is, during the analysis, they found that the tobacco had a protective effect. But the thing is, we have to wait until the 2006 to find that there is an unmeasured confusion uh, which can explain this paradoxal effect of tobacco. And this confusion cannot be controlled even if we randomize the exposure here to tobacco, even if we randomize that, since it will not be affected by the randomization because it's only appeared in the relationship between the weight of a baby and the infantile mortality. The other problem is the interaction between exposure and mediator, because the first equation that we saw is that there is no interaction term. But the thing is, if we didn't put this interaction term on the model, there can be two scenarios. The first one will be that the real effect, that there is a real effect of A, such as the coefficient beta 1 will be a difference of 0. But our model will estimate this effect as 0. And the other scenario is there is no effect of A on M and Y, but our model will estimate a significant coefficient. And to illustrate this problem, I just put here a very simple example for a binary mediator. If beta 1 is 0.5 and beta 3 -1, we can see that in the presence of a mediator, M equal 1, we will have a negative effect of the exposure, and in the absence of a mediator, we will have instead a positive effect. So to counter this problem, to try to solve this problem, we can add an interaction term on the model. So this is what we've done here, and it's complexify a little bit our estimation, but still it's identifiable, and we can calculate it easily on adding a second term on the direct effect and also on the indirect effect. But the thing is, we have to fix the value of the exposure and all of the confounding when you try to calculate those different effects. And it's easier on the binary setting with the exposure because you can just fix the level of A at 1 and A star at 0 as reference value. And also it's getting more complicated with a logistic regression. Here with a binary outcome. Tyler will propose that we put another extra term on the direct effect if we want to estimate the odds ratio, but it's pretty much the same for the indirect effect. But moreover, instead of the two main problems that we saw earlier, and when we try to correct this by adding some interaction term on the model, there is another problem, which are what can we do if we had multiple mediators on our model and also multiple interaction between the exposure and the mediator, and also between the mediators themselves. And also we wanted to decompose all of the effects, such as I just want maybe specifically this effect or this one with or without interaction. And also, since we are adding another covariates on the pathway between A and Y, we will have to control the different confounders for each association. And also we could have another problem with unmeasured covariates and confounding. And lastly, the non-collapsibility of OR with logistic regression, that we can't put a lot of covariates on our model because mathematically we can have a change in coefficient values even if some of the covariates are not confounding. So to try to address all of this problem, some researcher proposed to apply a causal inference approach to the mediation analysis. So to do so, maybe I thought it would be easier if we do a quick reminder of what is the causal inference field and what we call counterfactuals. And let's consider a binary intervention, such as if you have the intervention, you have A equals 1, And if you have not the intervention, your A will be equal to 0. And here I take the example in the causal inference book by Hernan and Robbins, which is the heart transplant. And also, let's consider a binary result, which is the mortality over 1 year after intervention, the heart transplant. And the thing is, for each individual, you will have the outcome, it could be 1, coded to 1, or the outcome will be coded to 0 if you are dead or not. So the thing is, for each individual, if you are not exposed, you will have a certain value of your Y, noted here Y not, and you will have, if you are exposed, you will have an overvalue of Y1. And in the real life, you can't observe these two outcomes at the same time. And that's what we called a counterfactual results or a potential results. And this is the fundamental problem of causal inference, because on the individual level, we can't have these two observations. We can't estimate the counterfactual at the same time. But at the population level, we can't estimate something which are the population causal parameters. And for that, on the binary outcome, we will estimate the classical parameters such as risk difference, risk ratio, and odds ratio. But in the causal inference field, it's like here, I put here that the probability of Y1 equal 1, it means that um, if all of my population undergone the intervention, for our example, it's a heart transplant, what will be the probability of death? And I will compare it to the probability if all of my population uh, had not undergone the heart transplant, which means that I will have to compare my outcome if all of my population are exposed versus if all of my population are not exposed. And once again, in real life, it's not possible. Also, if my outcome is continuous, instead of the probability, I will have the expectation of my outcome. Once again, if my entire population is exposed versus if my entire population is not exposed. The thing is that, as I said before, on the individual level, it's not possible to estimate the counterfactual, but on the population level, with some assumptions, we can't estimate those parameters. And usually during our study on the real life, we have a statistical parameters. It means the conditional expectation of Y, and what we want to estimate is the causal parameters, the counterfactual expectation of Y according to a level of treatment. And as I said before, if we respected several conditions, we can be in a situation that our statistical parameter is equivalent to our causal parameter, such as the the average of our outcome in which group of treatment will be equal to the average of the counterfactual in all of the population. So the only case we can have this equivalence in epidemiology is with our gold standard study, which is the randomized controlled trials. When we can define when we have a good definition of our interventions, and also if our randomization is well done correctly, we can compare directly different group, but because they are a representation of overall population. But the thing is, we cannot always do a clinical randomized trial. And most of the time, we can even do an experimentation. It's very frequent in epidemiology and public health. So we kind of lost the equivalence between our statistical parameters and our causal parameter. But we still wanted to answer causal questions from an observational study. So a lot of researchers developed a set of principles and methods to try to recreate the same condition as in a randomized controlled trial setting. And I've just here, I just put it here, the main methods we used in causal inference, such as the propensity score, J-computation, target maximum likelihood, and marginal structural models. And once again, if we are able to respect the causal assumptions, our counterfactual parameters is identifiable by estimating the statistical parameters. So what are those causal assumptions? So we can see them here. The first one is the no interference assumption, the consistency, the positivity, and the conditional interchangeability. Those assumptions can be a little tricky to understand, but what I wanted to do here is to very simplify it. So for the no interference assumption, it's just that your participants on your study shouldn't affect each other, such as if I expose one person, this exposure shouldn't affect other people exposure and other people outcome. The thing is, especially in infectious disease, uh, this assumption cannot be respected, uh, especially particularly if with people under the same roof, because when someone is getting sick, there is a higher probability for other family member to get sick too. For the consistency assumption, uh, it, it it is well explained by the fact that your exposure need to be well defined. Uh, this assumption can be violated when there is a lot of version of a treatment, such as uh, by getting back with heart transplant example. If you are a different surgeon, different techniques, procedures, and different teams, maybe you can the consistency assumption is not respected. For the positivity assumption, um, the thing is that all of your participants should have a non-zero probability of being exposed. For example, if you're doing a study on the effect of a treatment on pregnancy, for example, you have to make sure that all of your participants are female and they didn't have another pathology who can stop the pregnancy. And also, they shouldn't have contraindication for the treatment. And the last one is the conditional interchangeability, um, which is better explained by the fact that your group should be comparable since they should represent the overall population. So you should measure all of the confounders. So what is the impact of the causal inference approach on mediation analysis? Um, we, it's just an extension of the Baron and Kenny product method, but the causal mediation analysis allows us to better decompose the total effect. So it proposes also a solution to the confusion and interaction problem. And the main advantage is that we can define non-parametrically the effect. So it's not mandatory to apply a model-based approach, but since we define first the parameters, and after that we can apply different method to estimate this parameter later. And I wanted to show here the different parameter, so-called the counterfactual in the mediation analysis context. The first one will be the counterfactual if I fix the treatment at a certain level. Once again, it's easier in the binary with a binary treatment, such as we can fix A as 1 or A as 0. And after that, the second one is the YAMA, which is the counterfactual outcome, the potential outcome if I fix the treatment at a certain level, 1 or 0. And if I fix the value of a mediator at the value, if I fix the treatment at a certain level, it means that, for example, if I fix for the treated, what will be the outcome if for the treated, and for the value of the mediator, if in this group of treated people. The last parameter is a little bit counterintuitive. Uh, uh, Here we got the potential result if we fix the treatment on a certain level, and if you fix the value of the mediator on if the treatment if a treatment has fixed on another level. The thing is that since we are in on a counterfactual setting, it doesn't make sense at the beginning. But if you can imagine that you can observe a lot of counterfactual things at the same time, it does make sense since we do not have only the exposure and the potential outcome, but also the mediators. So at the end, we can decompose the total effect as the indirect effect, which we can like block in the effect of the exposure here at one, so we can have only the effect of the mediator. And also the direct effect, it's the other way. We fix the mediator effect here, so we will only have the effect of the exposure. But I will get in detail, more in detail later. And yeah, as I said before, since we are defined non-parametrically our counterfactuals, we can apply different methods to estimate them. But to get more in detail, we can also estimate the control direct effect if we are fixing the mediator at a certain level. It doesn't necessarily make sense with a binary mediator, but it makes more sense with a continuous mediator. And in order to block this effect of the mediator, you have to fix it at a certain level, and that will give us the control direct effect. The natural direct effect is defined if we are fixing the mediator level at zero, and it's kind of blocking this pathway, and we will only get the value of the treatment effect just only for the exposure, and the other way around for the indirect effect. If we are fixing the value of the exposure, we will only have the effect of the mediator. I've talked before about the four assumptions for causal inference, and it's getting more complicated on the mediation analysis because since we have another covariates on the pathway between A and Y, we have to control all of the potential confounding for each relationship. So that's given something like that for the condition of interchangeability. The first one, we'll have to control this confounding factor between A and Y. The second one is the confounding between the mediator and the outcome. The third one will be the confounding factors between the exposure and the mediator. But since we have, as I said, something else on the pathway, we also have to make sure that the confounding between May and Y are not affected by the exposure. It can be very complicated to control, so sometimes we can just have the control direct effect by fixing the mediator at some level. So we will just have to control for the confounders between the exposure and the outcome, and the confounders between the mediators and the outcome. And why we have to complicate our life with all of this equation and all of those steps? Because the mediation analysis can give us a very precious insight, like if we asking the question on which pathway had the greatest effect on my outcome, it's really relevant when you have a lot of mediators. So if you are asking the question like which one of my mediators are the more important on this relationship between my exposure and my outcome, and the second question is that what is the effect if I am blocking some mediators? So it can be very important in public health, as if I can block um, the level of smoking at a certain level, uh, what will be the impact of this on my cancer controlling program, for example? And also, I'm really sorry, it's getting more and more complicated. Um, but there is also what Talleyrand we called a four-way decompositions that we can at the, that you can get more insight on what's going on with the exposure A and the mediator M, and also the multiple interaction. So to explain this in a better way, here the four-way decomposition and the CDE, as I said before, it's like you are blocking the path on your mediator, so you will not have the effect of the mediation and the interaction, just the direct effect. Also, you can have the effect of interaction only with here the term interest. And you can also have the effect of the mediation with the interaction. And lastly, with pure indirect effect, you will have the effect of the mediator only. So we've covered already a lot of things, and we can ask here I wanted to do a quick overview of the package available for doing causal mediation analysis in R. They all got their pros and cons, but the thing here, mediation is pretty simple, and we cannot do a lot in terms of interaction. But this is the only package we can handle multi-level analysis. We will see it later. I've already put I also put Medflex here because it given a very intuitive output, which is not always the same thing with other package. The multimediate one is very interesting because it can handle the interaction, but also it can give uh, each specific effect if you have multiple mediators. And the last one is the CMA verse package, which can do better the four-way decomposition. So on top of all of those little complication, we still have another one, which is the multi-level detached structure. So um, it's very frequent in the epidemiology fields that our observation can be grouped. Um, you can have your participants from different school, a lot of school, or your participant in a clinical trial from different hospitals. The consequence of that is that um, the main hypothesis on your regression model will not be respected, which is the independence of your observation and your errors. So it will have some consequences that you will have some error on estimating the variance, and you can also have an error on your hypothesis testing because you have to take into account the within group and also the variability between those groups. So in the literature, they proposed in order to solve this problem, the mixed effect problem. So we will have a fixed effect for all of individuals, but also we'll have a random effect, which depends on each group. So the notation of our outcome will change a little bit with our Y subscript, which represent the individuals at the micro level, and it will take the within group variability, and the J subscript, which is about the groups or clusters at the macro level, and it will take the information about between group variability. Here I wanted to show the impact of this a little change on our way to write our model. Since we have two levels now, the within group model is pretty similar as we've seen before. We still have intercept on our effect on our exposure, but the change here that we have to add a fixed effect on the level 2 and also a random effect, which is given this overall complete model. It's pretty similar on the simple regression model. We will just have here, as I said before, the fixed effect and the random effect who will be different from each other group with the J subscript. And also, we have to add more assumption of our model. Our residual errors will follow a normal distribution with a mean zero mean and a variance of sigma square. And also our random effect term will have another variance which had to be estimated by our model. And also to take into account, as I said before, the within group variability and the between group variability, we can change a little bit the variance covariance matrix structure for our residual errors. And for example, if I fix the number of group J at 4, we can see there that we can specify the variance of our group. We can say here, for example, that each group will have their own variance or the same variance here. And also we can set the relationship between the groups, such as if the groups are pretty close, they will be more correlated. And as the distance between the group grow, the correlation will fade away, will get smaller. So what is the impact of all of the stuff on our mediation analysis? So we can have mainly free setting. The first one is if the treatment is on the group level, the level 2, uh, the second level, and the second one, if also our exposure and our mediation are on the group level. And the last one, which is the more common, all of the exposure, the mediation, and the outcome are on the individual level, but still we have a multi-level settings. So the impact of that is that we have to change a little bit the notation of our Baron and Caney model-based approach. And the thing is, I didn't want it to be too much complicated here, but the first notation, I just put the capital of Greek letter, but it's pretty much the same as we've seen before. The only things that change here that we have to consider the fixed effect and also the random effect specific for each group on each parameters now. And here I just wanted to put the example. If I only put a random effect only on the intercept, but you can put the random effect also on each coefficient for the exposure, the mediator, and for the interaction terms. And also, once again, it will complexify a little bit our estimation because you have to estimate more parameters on our models. So I wanted to get back on the available packages because the thing is, doing a model-based approach can be a little bit complicated. We will see that later, but the over package, they are doing an imputation based. It means that they will predict the counterfactual directly, so it will be easier to estimate all of our parameters. And unfortunately, only the mediation package can handle the multi-level data structure. So with all of these things that we've seen, we wanted to apply that in a case study. So firstly, I wanted to introduce a little what we have done. So we've asked the question on how information type can impact future adherence to restrictive measures, and we apply that to the COVID-19 pandemic. And our study is based on the multi-jurisdictional survey of public health, pandemic-related trust, communication, and behaviors. It was an online survey using random domain intercept technology, and it was conducted by Real-Time Interactive Worldwide Intelligence Platform in Toronto. So they were able to draw the data from more than 100,000 participants from 11 countries. It was from September 2022 and December 2022, which are the main two waves of during the COVID pandemic in Canada, worldwide. So this is how our data and variable looks like. There was 14 question on during the survey, but we wanted to focus our attention first on this relationship. As exposure, we have here the primary COVID info source, and as outcome, the future compliance. And as you can see there, it's mediated. It is a causal a mediation structure with as mediator personal compliance, and the other covariates such as age, gender, education, and the other stuff are confounders. And here we take in the country as the main group. We've tried to do a free-level analysis, but it didn't work, unfortunately. About the participant of our study, the first thing is since the question were randomly assigned, the participant, it wasn't mandatory for the participant to answer for all of the questions. So from the 1,100 participants, we only had 2,300,000 observation with no missing value, which is pretty sad, but still we can do some analysis with it. The mean age was 37, and there was a large predominance of male participants with a sex ratio of 3. Most participants are from Canada with 3,000 participants, but the number from the other country were at average of 2,000 each. Most of the people lived in a large area, and more than half of the participants had a higher level of education. And we classified the primary COVID information source on 3 levels. For the international media, WHO and scientific publication were categorized as sure information source. The national media, TV news, radio as medium, and the podcast, social media, friends and family as low information source. And as you can see there, 45% of our participants used a medium source of information during the COVID pandemic. And also 73% of our participants said that they followed all or most guidelines during the pandemic, and 70% said that they will follow the guidelines if another pandemic will come. Also, they perceive that 60% of them say that many of the people in the community would follow the guidelines. And also, as a future information source, 30% say that they will reach for the health responsible, 30% for the government, 26% for the NGOs, and 10% didn't want to use any of the source of information. Also, around 60% of people trust the doctor's communication, and 52 trust the communication of a politician. So how did we implement the multi-level mediation analysis for this trust study? We used two packages, which are the LME4 package with the GLMER function, because as I said before, since it's a model-based method, you have to run the model first. So here we have our two model, the model for the mediator and the model for the outcome. And after that, we will put the output of this mediator on the mediate function of mediation packages, and after that we'll have the summary of the mediation analysis. One of a little problem with the mediation packages is that it had a lot of specification to be respected. The first one is that our outcome and our mediators had to be binary. And also, since we have a multi-level exposure, for each analysis, you have to specify the categories to be compared 2 by 2. It was also computationally demanding. It took us all day to do a first 2 by 2 comparison because you have to do like 500 simulation to get the interval confidence. And also, the output are not very intuitive. It's given the total effect, the indirect effect, which they called ACME, average causal mediation effect, and lastly, the average direct effect. But the thing is, for the binary outcome, the mediation package didn't give directly the odds ratio, but the total effect had to be interpreted as the increase of probability of developing the issue. So what did we get with our analysis? Firstly, I wanted to show what we've done in R. So here you can see the mediator model we put on the function, also the outcome model. We have to specify the name of the treatment variable and also the name of the mediator variable. And as I said before, since we have a multi-level exposure, you have to do a 2 by 2 comparison. So here we just wanted to take first the low quality information source as reference, and we want to assess the effect of high quality information source, and we've done a 500 simulation. So after 1 day, we can finally able to do a summary, and which is giving us something like that. And we always want to check if it was actually a multi-level mediation analysis, and on the output, it clearly says that it was a causal mediation analysis with groups from the mediator and the outcome as the country. And here we can see the total effect, the average mediated effect, and the average directed effect, and also the proportion mediated. That the thing is, it was a little bit disappointed. I didn't expect such a low value, but still, as I said before, the total effect will give us the information that our information source is significantly associated with feature adherence since it's strongly significant. And it can be interpreted as the increase, that there is an increase of 2.8% of probability of future measures adherence in people with secure source of information compared to people using a low quality source of information. I acknowledge here that this is not a really great improvement, but still the important thing here is the proportion mediated. It says a little that it's true that the information source can have an effect on the future adherence if another pandemic will come. But the thing is, the half of this effect is explained by the actual adherence of the people during a pandemic, such as if the people didn't adhere to the measures during the pandemic, they will likely not adhere to future pandemics, no matter the source of information which can be used. So this is our preliminary result, but I wanted to say something about the fact that we didn't have enough resource to, and we didn't have enough capacity to answer the question about the over mediators on our association between primary info source and future compliance. So the thing is that we had a lot of limitation on our study. The first one is the representativeness, since it's a voluntary sampling. Also, it's a self-administered questionnaire, and we only had the 14 questions, so there is a lot of confounding factors that we are not able to measure. And also, about the package, the multi-level mediation analysis cannot be done for the multiple mediators. And also we still have some struggles getting the specific information for each country. The result I've shown before is for the overall participant worldwide. And also we didn't find a package that can handle other types of output and mediators, such as ordinal, multinomial, continuous mediators, and outcome. So in conclusion, we can say that mediation is very important in epidemiology, public health, and the causal inference fields. That multi-level data structure is more and more common in our everyday researcher life. And the multi-level mediation analysis can be very complicated, and there are not that much statistical software who can handle it, which is a bit sad. So we really need further development of methods, just as to get the specific effect of each mediator when you have multiple mediators. Also to handle more the interaction between mediator and exposure, and the non-binary exposure and mediator, as I said before. So before concluding, I would like to thank Neil Seaman, who granted us the access for the data, and who is also one of the co-investigator of the primary study with Kumar Murthy. And also I wanted to thank Bushra Nasri and all of my lab team. Thank you.